Okay, so good morning, everybody. This is the last lecture in our course. So we were discussing how you simulate on a computer the Haar-Siegel measure on the space of lattices. So I want to remind you again something I discussed last time. So what does it actually mean? What do we mean when we say we want to simulate a measure on a computer? The computer, the space that we want to simulate the measure on is a uncountable continuous space. It's the space of lattices, and everything that's in a computer, at least as far as I understand it, is discrete, is finite. So what does this actually mean? And so the definition involves weak star convergence. So recall, want to simulate the Haar-Siegel measure, which we denoted by m of xn on xn, the space of lattices of covolume 1. What does this actually mean? So there can be several meanings that people give to this, but the standard one is you want a measures, n is a bad, you want measures on the space. So these are Radon measures, maybe probability measures, maybe not, such that nu j converges as j tends to infinity to the Siegel-Haar measure in the weak star topology. And what that means is for every function of compactly supported continuous function f, you want the integral of f with respect to the measure nu j to converge as j tends to infinity to the integral of f with respect to the measure that you want to achieve in the limit. And the nu j's should be something that you can should be or could be, let's say, could be finitely supported measures, in some sense approximating better and better as j, the parameter j tends to infinity, this continuous measure. F is called the test function. So for every test function individually, you want this, this is a convergence of numbers, and you want this to happen. And if this happens, we say that we have weak star convergence. So another way of thinking about it is we have a Riesz representation theorem. So measures are nothing but linear functionals, and this is the value of the linear functional corresponding to nu j on f, and this is the value of the linear functional corresponding to the Siegel-Haar measure on f. So let me just give an example for those of you who are not so familiar with this. Maybe most of you are, but some aren't. So let's just do an example, and this example will be useful also in the future. And also let me, before doing the example, I'll just mention that sometimes we also want a rate of convergence. To say that we have a control on the rate in this formula here. All right, so let's do a very basic example. So x will just be r, the real line. The measure we put on r will be the Lebesgue measure on r. Nu n, my parameter is not j now, it's capital N. Nu n is 1 over n sum I goes from 0 to 2 times n squared. I'm sorry. we have a set consisting of 2 times n squared points. Here's the set. So I'm taking the interval from minus n to n, and I'm dividing it into little pieces of size 1 over n. Actually, this is 2 times n squared plus 1 points because of these 2 n points. And I'm evaluating the function, the integral of f with respect to nu n is 1 over n sum I goes from 0 to 2n squared f at the point minus n plus I over n. Okay? And I claim that this converges to the Lebesgue measure on R. I'm going to
Barak,
prove that.
can I pause you for a question? Sorry.
Sure, sure.
So in the beginning, you were in a specific case where we spoke about the space of lattices, and now
Right.
you give an example of a general
I'll
set
give you an
of.
example on a different space. It's which is the real line, just
Mhm.
to make the intuition easier.
The
And
intuition
this
in
is
terms
actually
of a Lie group, and then
no. The intuition in terms of what this weak star convergence means. So
okay.
this is for me, the real line is a simple space. The space of lattices maybe is a more complicated space. In general, this definition here, you should use this definition whenever you have an LCSC space, a locally compact second countable space.
Okay.
So now, before I do the proof, just notice that there are 2 times n squared points here, but we are normalizing by 1 over n, not by 2n squared. So this is not a probability measure. We have 2 times n squared points. Each of them is being given weight 1 over n. So this is not a probability measure. And indeed, this is not a probability measure either. So this is sort of makes sense. And what we're scaling by is the number of points. 1 over n is basically the number of points on every, on the unit interval, on a unit interval for the measure. So let me just make that remark because this will be important. Scale by number of points in a unit interval. Right? The points are spaced 1 over n apart from each other. So in an interval of size 1, there are capital N of them, and that's what we're scaling by. Okay, proof of the claim. So suppose f is our test function. It's compactly supported and continuous. Let's just say the support is contained in some interval AB. And so the measure that we are trying to, I'm claiming that we approach the Lebesgue measure on the real line. This is our notation for the Lebesgue measure, which is just the Riemann integral of the function on the interval AB. And let's say that n0 is large enough so that for all n bigger than n0, the interval AB, which is the support of our function, is between minus n and n. So here's the picture. Here's the real line. Here's maybe the interval AB. The graph of the function maybe looks like this or something. And the points in our, the points that we're using are kind of very evenly spaced points, distance 1 over n apart. And we're sampling the function at those points. So the integral of f with respect to nu n is the is 1 over n sum f of so this is I from 0 to 2n squared. This is the definition of the function nu n. And this is just, this is the Riemann sum for f corresponding to the partition. So if we put if you recall the definition of the Riemann integral, in the Riemann integral you have a sum, a finite sum, where you're taking the values of the function at certain points of a partition, and you're multiplying the values of the function by the lengths of the intervals in this partition. The lengths of the intervals in this partition are 1 over n. So this 1 over n is the distance between 2 points in the partition. And we know just from the definition of the Riemann integral that this sum converges. So this is as n tends to infinity to this interval. This is by the definition. Well, no, maybe not the definition. Okay, let's remove the word by definition. Yeah. So if you recall your first course in integration, maybe you took a course where you start with Darboux sums and then you talk about Riemann sums, or maybe you start with Riemann sums and then you talk about Darboux sums. This is the Riemann sum and it converges. All right, so this is how this works for this. So this is a finite distribution, which as n gets larger, gives us a better and better approximation of the Lebesgue measure. Let's talk about the rates for a moment. So I said that you sometimes want to talk about the rates. Suppose the test function f is Lipschitz. So that means that there exists a positive c such that for all x and y, f of x minus f of y is less than c times x minus y. So this is a property of the function. Then on each of the intervals in this partition, let's say y plus 1 over n. This is one of the intervals in the partition that we had before. Y is the endpoint. If you look at f of x minus f of y, this is less than, so x is some point in the partition. So the distance from x to y is less than 1 over n. So this is c times x minus 1, which is less than c times n. And now if you look at the integral of f restricted to this small interval, and you subtract f of y, take the absolute value, this is less than or equal to putting the absolute value inside. This should be a dx. We get that the difference in the integral on every subinterval is less than c over n squared. And so the difference here so this is this is less than or equal to, on every interval we get an error of c over n squared at most, and the number of intervals which intersect the support is n times b minus a. So in total, we get the error. We get an explicit bound on the error, and this inequality here is because if the interval that we're looking at doesn't intersect the support of the function, the error is 0, and otherwise it's bounded by c over n squared, as we saw. So this is the error on each one of those small intervals that intersect the support. This is the number of intervals that intersect the support. And so this is a bound on the error in terms of c, which is a Lipschitz, which is the Lipschitz constant of the function, b minus a, which is the support of the function, which is the size of the support, and then this n, which is measuring the quality of the approximation. So that's how these estimates work. You have a rate, here it's 1 over n, times a constant which depends on some properties of the function. And in this case, the properties that we care about are the size of the support and the Lipschitz functions. And so you're seeing that this doesn't happen, this error bound doesn't hold for all functions. It holds for Lipschitz functions. In general, when we talk about error bounds, we're going to be restricting our test functions to special classes of functions, and then we'll get an error bound. In general, you can't expect to have an error bound which is good for all continuous functions. And the reason is that you can always take a, if this is nu n, I just want to sort of invent a function where the error bound is bad for this particular n. Well, I take a continuous function and I just make it, very, very large on a very, very small set. And the finite distribution is not going to see this function at all. It'll give it integral 0, no matter what the actual integral of the function is. So you should always have some relationship. If you want to talk about error estimates, there has to be some information about the function so that this type of counterexample can't be cooked up. All right. So that's just kind of, any questions about this? That was just some kind of general remarks about what it means to simulate measures.
Yes,
Okay,
maybe.
so now, yeah.
So regarding what you've said now, in terms of the computer science intuition, what will be what's the importance of the measures that you can have a rate on it?
I don't understand the question.
I understand mathematically that there are some measures that for some of them you have this that you can bound the rates.
Mm-hmm.
But if you go back to where we started the discussion,
Mm-hmm.
Of the discrete measure that we want to use in terms of the computer science.
Mm-hmm.
So what will be these functions, these functions that we can have a rate on the convergence?
So the answer, okay, let me give the example and then I'll answer your question. Okay, maybe it'll be easier. So how do we do this in for lattices now? So simulating Harzigel measure. So this is some technique that's called using the so-called Hecke correspondence. So, which I'll explain now. So you start with any lattice in the space of lattices of covolume 1, dimension n, and you let P be a prime. And P is playing the role of the parameter n, so or j. So P is going to become larger and larger to run this simulation. And we have another lattice of covolume 1, L prime, and it's called a Hecke friend, a P Hecke friend of L0 if there's a sublattice L1 of L0 of index P. So this is a lattice of covolume P. It's not a lattice of covolume 1, but if you rescale it, and the proper rescaling is by the uh, uh, scalar p to the power minus 1 over n, you get L prime, right? L1 has covolume p, L0 has covolume 1. L1 is of index p, so it has covolume p, and now we're making it denser by this factor, p to the minus 1 over n in each direction. Dimension is n. So L prime has covolume 1, and so L prime is derived from L0 by taking a finite index, an index p sublattice and rescaling. And then the measure, nu p, is 1 over np. Np is the number of such sublattices of Hecke friends. So L prime is p Hecke friend of L0, and we take the Dirac mass at L prime, where np is the number of p Hecke friends of L0. The number of p Hecke friends of L0 is the number, any lattice has the same number of p Hecke friends. It has this description has nothing special to do with the properties of the initial lattice L0. And it's easy to compute this number, but I won't do it. I think it's one of the exercises on your exercise sheet anyway, and it's not really important for our discussion right now. So this is a probability measure because I'm rescaling by the number of elements here, and it's spread out over the index p sublattices of L0 rescaled. And so let's prove that this, so proving that this actually converges weak star to the Haar-Siegel measure is beyond the scope of this course, so it's not a trivial thing. But I want to prove a kind of a somewhat weaker statement, and you'll see, you'll understand what the more difficult part of the proof is. And so we will prove a weaker form. We will prove this convergence. This is the definition of the convergence that we talked about, the weak star convergence. But instead of proving this for all continuous functions of compact support, we'll prove it for another collection of test functions. So these are the test functions that you get in the Siegel summation formula. So f of L equals sum v in the non-zero vectors in a lattice L of phi of v, where phi is a compactly supported continuous function on Rn. So remember, we had a Siegel summation formula saying that if you take functions that look like this, then their integral with respect to the Siegel-Haar measure is the integral of phi on Rn. This was the Siegel summation formula. And now we're taking such functions as test functions. So these are certainly not all functions on this space arise, not all the functions that we care about in the weak star convergence arise in this way. And also these functions, they are continuous, but they're not compactly supported. It's not true on the space of lattices. If you have, if your lattice L has short, suppose phi, for example, contains is one around in a ball, is positive in a ball around the origin, then all lattices with a short vector will contain a point in the support, and this will not be zero. So that means that this function f is not compactly supported. That's kind of the typical situation. Nevertheless, we're going to prove this, let's call this star. We're going to prove star for these test functions because it's just because we can, it's easier. And also these are functions that sometimes show up when we want to understand lattices. So let's do that. So the integral, so proof of star for such a function f. So the integral of f with respect to nu p is 1 over np sum L1 of index p in L0, f of p to the minus 1 over n L1. This is the definition of the measure nu. And now I'm going to plug in the definition of the function f. Okay, so this is just definitions. And now I'm going to divide this sum into two types of vectors. So let's just recall here that we have, maybe I'll write this over. Okay, I'll write this. I'll leave some space here for explanations, and I'll divide the sum into two pieces. All right, so what I did was I took this sum. So we're summing here over all vectors which are in L1 rescaled by p to the minus 1 over n. And I want to divide these vectors into two kinds. And the two kinds are, so let me just write this down here. We have this kind of an inclusion. We have L1, and it's contained in L0 in index P. And since it's contained in L0 in index P, if you multiply L0 by P, you get a sublattice which is contained in L1. Because every element, if you think modulo, if you think of the projection of L1 onto, of L0 onto the quotient, every element is of order P because the index is P. So multiplying every element by P, you get into L1. So because of this inclusion here, we can divide these vectors into those that belong to P times L0 and those that don't. So those that don't are just here. Okay? And those that are, since we're multiplying them by P, I've put this extra factor of 1 over here. Okay? So this is the division of the sum into two pieces. And I'm going to separate this into two sums. So first, let me copy this. And then I'll explain. Oops. So what I did is I copied this term with this average, and then I copied this term and I omitted the average. There's no average on the left-hand side. You see here, there's this expression is the same as this expression, and I removed the average. And the reason I removed the average is because here I'm averaging over all the sublattices L1, but there is no L1 in this sum. This sum this sum is completely independent of L1. All the L1s contain this, so all of them contain this. So this sum appears in all of them, and the averaging just gives the same sum back. So we get this. Maybe I'll write that down. Put that explanation down. So first, summand does not depend on L1. So averaging on L1 can be removed. And let's call this expression A, and let's call this expression B, and let's analyze these two expressions separately. So first of all, regarding A, so if P is large enough, any vector in P to the power 1 minus 1 over n L0, which is not 0, is outside the support of phi. Right? When we increase P, these vectors are becoming longer and longer, and we're evaluating them on phi, which is compactly supported. So for P large enough, this sum is 0. So A goes to 0 as P goes to infinity. It just becomes, eventually it just becomes 0 when P is large enough. And in in the sum B, let me write a claim and I'll prove it later. Claim in the sum B, every vector V in L0 minus P of L0 is chosen with the same frequency. So let me explain what I mean by the claim. I'll prove the claim at the end. So what is B? We're summing twice. First, we choose L1. And then when we choose L1, we take a vector which appears in, this should be an L1, I'm sorry. Did I miss that? Yeah, this is L1 right here. Oops. L1 right here. So this is, so what am I doing? I'm taking the vectors V, which I'm choosing my L1s, then I'm choosing the vectors V, which are contained in L1 and they're not contained somewhere else. And I'm doing this over and over again for all the L1s. So some of the Bs are chosen for some of the L1s, and I'm claiming that every V, which is outside of PL0, is chosen with the same frequency. So that's what this says. Okay. Let's believe the claim for a moment, and I'll prove it at the end. So assuming the claim, let's compute the frequency. In other words, how many times does V get chosen in the sum? So there's a total of Pn minus 1 vectors. So there's, what do I want to say? Okay, we're going to see, let's just add that to the claim and I'll prove that later. So the frequency is going to be this number. And I'll prove that at the end. So let's assume that this is the frequency. And so then what's B? B is the frequency that I just wrote down. multiplied by this sum. Oops. All right, so let's look at this number. This number is, when p is large, this number is almost exactly 1 over p. So I'll just rewrite this as 1 over p and add an error term at the end. So 1 over p, and here I'll write plus little o of 1. And I'll also make a change in the sum. Oops. Okay, so I made 2 changes, and I'm claiming that these 2 changes only affect the sum by something that goes to 0 when p goes to infinity. So what are the 2 changes? The first changes is that this term was replaced with this term. And you see that when p is large, these 2 terms are almost equal to each other. The second change is that I added back the elements of PL0 to the sum. So here in this line, they're being removed, and this line, they're not being removed. So what's the difference between the sum with these elements removed and the sum with these elements not removed? Well, if the vectors are non-zero, we already saw that they're outside of the support of the function. So they don't change anything. They add 0 to the sum. And there's only one element which we're actually adding, which is 0. So 0 is, there's a number phi of 0, and phi of 0 divided by p goes to 0 when p goes to infinity. So that's the explanation. Let me write that down. So 1 p, this thing is this thing plus something going to 0 as p goes to infinity. And also added back to the sum the vectors v in p 1 minus 1 over n L0, all but one of them, namely the vector 0, don't belong to the support of phi, as we saw, for large p, and don't affect the sum. Okay, so that's why we have this. And now let's think about this sum. So what is this sum actually? This sum over here. So we're taking a lattice. We are rescaling it by p to the minus 1 over n. So this means we're making it very, very dense. And then we're sampling a function at this dense collection of points, which are evenly spaced on a dense lattice, and we're dividing by p. P is the number of points in a unit a cube for this lattice. The lattice is denser by a factor of p to the minus 1 over n, and we're in n dimensions. So this is the average number of points in a unit cube, and we're sampling a function. So this is just a multi-dimensional Riemann sum for this function phi. So I'll write that down. So this tends, as p tends to infinity, to the integral on Rn of phi d Lebesgue measure. Again, why? This is the Riemann sum. That's the argument that we saw at the beginning of the lecture. Think of this integral as a Riemann integral in Rn. And so this is a Riemann sum. You're sampling the values of this function on a partition into small parallelepipeds corresponding to the fundamental domain of L0. And 1 over p is the number of points per unit. It's the volume of each of these small parallelepipeds. So this convergence here, again, is by definition of the Riemann integral. And finally, this last number is the integral of f on the space of lattices, and that's the Siegel summation formula, which we proved before. So all of this taken together gives us that b tends to the integral of f, a tends to 0, and so this sum, which was this expression, tends to the integral with respect to the Siegel-Haar measure, and that's what we wanted to prove. The only thing remaining to prove is this claim. So the claim was that in B, this claim here, in B, every element is chosen with the same frequency, and this is the frequency. So this is this expression B. Okay, so let's prove this claim. So let's think about the quotient of all of these vectors lie in L0, but none of them lie in P times L0. We're just taking those that appear in sublattices of index P, but they're not in P times L0. So the best way to think about this is to project everything to the quotient L0 over PL0.
Sorry.
So, yeah.
Can you? I'm missing. Why do they all lie in L0?
The
vectors,
all the
so
vectors.
L1 is a sublattice of L0, but then when you
Right.
rescale it by P to the -1.
I'm sorry. Yeah, you're right. Forget about this rescaling. I meant these points. Yeah, you're
Okay.
right.
Okay.
They're rescaled, but all of these points all lie. I'm going to think about them as if they all come from a rescaling, as you said, of L0. And so I want to think about them as being elements of L0 modulo P times L0 rescaled by this factor. Okay. So proof of the claim. Let's consider L0 over P times L0, where all the V in the sum. All right, let's not say that because of Manuel's objection. So I think of where these V's project to in this quotient. So what is this? So just as a group, so L0 is isomorphic as a group to Z to the N, and you're quotienting by P times Z to the N. So you can think about this as this group. Additive group, abelian group, which you can also think of as Fp to the N. Fp is the same set, but I think about it as a set with two operations. It's a field now. So this is the field with P elements. So as a group, this group, as an additive group, this group is exactly like the additive group of this vector space. Now, what is a vector subspace? In a vector space, it's closed under addition and it's closed under multiplication by scalars. So all the subgroups, oops, I'm sorry. So all the subgroups just become subspaces, right? I mean, again, what is a subspace? It has to be closed under addition. Of course, subgroups are closed under addition. And it has to be closed under multiplication by scalars. How do you multiply an element of this thing by the scalar, I don't know, 5 mod p? You just add it to itself 5 times. In general, you have to add it to itself at most p times, and you get all its multiples by all scalars. And so so a group is actually a vector subspace. So any subgroup of L0 mod PL0 is actually a vector subspace. And so the projection of L1. L1 is an index P subgroup. The projection of L1 to this Fp to the n is a subspace of dimension n minus 1 in this discrete vector space. So what we're actually summing over, so each V is counted according to the number of n minus 1 dimensional subspaces containing it. Now, in a vector space, each non-zero vector is contained in the same number of, in a finite vector space, it's contained in this, in a vector space over a finite field, it's contained in the same number of n minus 1 dimensional subspaces, right? Because SLN of Fp, if you like, SLN of Fp permutes the vectors and the subspaces and acts transitively on the vectors. So every vector belongs to the same number of n minus 1 dimensional subspaces. So that means that every V is sampled the same number of times. In the sum B. And what is this number of times? It's the number of non-zero vectors in this space times the number, in the denominator, and the number of subspaces in the numerator. So number of subspaces of dimension n minus 1 in this subspace. The number of non-zero vectors is p to the n minus 1. All the vectors, there's p to the n total number of vectors, p to the n minus 1 are the non-zero vectors, and the number of subspaces, p to the n minus 1, because counting subspaces is the same as counting, how to say this? Wait a minute. Sorry. I didn't mean number of subspaces. I meant the number, sorry. It's the number of non-zero vectors, sorry, in an n minus 1 dimensional subspace. So the number of non-zero vectors in an n minus 1 dimensional subspace is this number. So you're counting how many times each point is counted. You're going over each of the vectors. That's this denominator. And for each of the vectors, you're seeing how many each time you choose a subspace, you're choosing p to the n minus 1 vectors out of the total number of vectors. And so on average, each vector is chosen with this proportion, because that's a proportion of the vectors you're choosing every time you choose a subspace. Okay, so that proves the claim.
Can I?
Yeah.
I'm not sure I followed that, but I have a different question. Isn't the number of n minus 1 dimensional subspaces the same as the number of 1-dimensional subspaces?
Yes, so this is another argument for this.
Okay. Yeah, okay.
Yeah. But yeah, if you pass the dual space, that's exactly what you see. But I mean, okay, yeah. All right, so that proves the claim, and that proves this equidistribution statement. Let me just add one, before we take a break, let me just add one more thing, which I was planning to talk about, but then I decided to put it in the exercise sheet. So let me just tell you about another way of simulating this measure, this Harzigel measure, is called equidistribution of horospheres. I just want to very, very briefly say what's going on, and there's more in the exercise sheet. So let GT be this matrix, e to the t, e to the t, e to the minus n minus 1 t. This is a matrix in SL and R. It's a diagonal matrix. Everything away from the diagonal is 0. Let's let UA, where A is a vector in the unit cube of dimension n minus 1, and we write it as an n minus 1 tuple. The vector is, you have ones on the diagonal, zeros below the diagonal, and then you put the numbers a1 up to an minus 1 in the right-hand column. So that's the vector UA. And you can define a measure. So nu of t, so the define nu of t on this space of lattices by the integral of a function f with respect to nu t is, well, you just integrate f on the unit cube. In other words, you take f and you evaluate it on these lattices. So L0 is just the standard lattice Zn, and you take the standard lattice L0, you push it by this matrix UA bar, and then you push that by the diagonal matrix GT, and that gives you a lattice, and then you integrate the function with respect to the Lebesgue measure on the lattice. And the claim is, so theorem, this is what's called horospherical equidistribution. These nu t's converge as t tends to infinity to the Harzigel measure in this weak star topology. And this is something that I proved in the homogeneous dynamics course that I gave last year for those of you who took part in that course. But it's also exercise, on the exercise sheet, what I asked you to do is something similar to what we just did. I asked you to prove this not for all test functions, but for the test functions which arise from the Ziegel summation formula. So test functions that look like what we just discussed. Where did this go? Yeah, test functions of this, for test functions of this form, proving this equidistribution statement is somehow easier and more geometrical, and you don't really need to understand dynamics on the space of lattices to prove that. So that's on your exercise sheet. That's a nice exercise. And final thing to say is, in all of the statements that we've been discussing, so in other words, the equidistribution of the Hecke, of the simulation coming from the Hecke correspondence, and with the horospherical equidistribution, you can get rates. The rates are usually given for compactly supported continuous functions on the space of lattices, and getting the rates and optimizing the rates involves a lot of mathematics, some of it rather deep mathematics. But for this class of test functions, you can get effective rates. So the arguments that the entire argument that I gave here is very easy to effectivize, and you get a rate for these functions. The argument that you'll see for the accurate distribution in this case is also easy to effectivize for the same kinds of test functions, and you'll get a rate there, and the rate is actually very good for those particular test functions. So that's what I wanted to say about simulating the Har-Siegel measure. Questions before we take a break? Any questions? All right, so let's take, yeah.
I have a question. So basically, this proof, the proof they just showed that choosing a prime p and taking the limit as p goes to infinity. So say we could also go. The proof also works with things that say have very large prime factors, right? I mean, say a product of two primes.
Right.
Actually,
the proof even works for every m, every integer. You can talk about, there's a whole class of things. So I call this Hecke correspondence and defined Hecke friends. And I gave something which is actually a very special case. So what I talked about is all sublattices of index p. You can also talk about all sublattices of index m, where m is an integer. You can also talk about all sublattices of index m, where m is an integer, and the structure of the quotient group. So there's a quotient group L by the lattice, and it has a structure as an abstract abelian group, and you can sort of fix the structure, and look at all such sublattices of index m. That's a collection. And you can do the average on that, and you'll get the same answer. It's just more complicated to prove. And there are variants. Instead of taking sublattices, you can talk about superlattices, which contain your initial lattice in index m or index p, and that's also called part of the Hecke correspondence. So the Hecke correspondence is actually kind of more general than what I described.
These are kind of like Hecke operators.
This is the Hecke operator. This is the Hecke. What we're doing is this is the Hecke averaging operator. Let me, yeah. Since you've asked, let me just say what is a Hecke operator? So the Hecke operator is an operator. Maybe T is a good letter. TP. It's an operator on this space. Okay. Well, this is not a Hilbert space, or it's not even a Banach space. So sometimes you might look at the action maybe on this space. Maybe that's kind of more standard. Okay. And the operator, one example of a Hecke operator would be the averaging operator that we just did. So TP of phi. Phi is a function. Maybe phi is a bad symbol because I already had phi a moment ago. So psi now is a function, say in L2 of the space of lattices. And so TP of psi evaluated at L would be psi at L1, exactly where, psi of P inverse of L, P to the minus 1 over N of L1, where this holds, say. Okay, so we're averaging a function on the space of lattices on the Hecke friends of a given lattice. And so this is just an example of a Hecke, of one of the Hecke operators. The other Hecke operators are sort of parameterized by something called double coset spaces for S, L, and Z, and this is just an example. Okay, so these are called the Hecke operators. So they're very intensively studied in analytic number theory. Okay.
The effective equidistribution of Hecke points.
Yeah.
This is more difficult than effective equidistribution of horospheres, right? It also uses the whole.
I don't believe
Or
so. I think it's
is
more or
it the
less the same.
same scale of difficulty? Okay.
Yeah, they both basically use property T or some spectral estimate, and
And okay,
they're quite similar actually.
okay, but
And they're much easier for these. They're much easier for these particular functions that arise by Siegel summation, both of them.
Okay.
It's completely parallel story.
Okay.
All right, let's take 10 minutes and do something different. All right, let me continue. Please just raise your hand so I know that you can hear me. Thank you. Okay, so I want to talk about another. We spent most of the time in this course discussing the packing density or lambda 1 of a lattice. How do you find lattices with large lambda 1? There's a kind of a dual problem, which is also very interesting and somewhat different. And it's about the covering volume and the covering density. So covering volume and, covering volume and the covering radius. So what are these? These are two geometric numbers associated with the lattice, and they have the relationship between the covering volume and covering density is similar to the relationship between the packing volume, which we discussed, and the short length of the shortest vector. So these are two numbers that carry sort of the same information in different guises. And so what's the covering radius? So if L is a lattice, the covering radius of L, which I'll denote by covrad of L, is the inf of the positive R, such that if you take the union of balls of radius R centered at lattice points, you cover space. So this is the Euclidean ball in this definition, but you could also make the definition for other norms or other convex bodies. But in today's discussion, we'll talk about the Euclidean ball. And equivalently, this is the maximal distance of a point which is in Rn, which is not in the lattice, from a point of the lattice, right? So okay, so you can convince yourself that these are actually the same numbers. So the furthest, somehow the point in Rn, which is furthest away from a lattice point, is called the dipole, and it's the radius of a ball around the smallest radius of a ball around lattice points, which will cover in all of space. And the covering volume sort of measures the same quantity. It's usually denoted by this capital theta. Capital theta of L is the inf of the volume of B, where B is a Euclidean ball, and B plus L is Rn. And so we know even less about the behavior of these quantities for large dimensions n than we do for the corresponding packing numbers. I mean, this is sort of completely mysterious how these numbers, how these densities behave, and also how to explicitly construct lattices for which the covering is efficient, just as it's hard to find lattices for which the packing is efficient. So if you remember, I said that the packing the lattice is realizing the packing density, and the packing density, they're only known as in dimensions 1, 2, 3, 4, up to 8 and 24. So there are very few dimensions in which they're known. The covering volume or the covering radius. So here the name of the game is to minimize the covering volume or minimize the covering radius for lattices of covolume 1. The covering problem is only solved in dimensions, in fewer dimensions. I think it's 1, 2, 3, 4, and possibly 8 and 24. Also the same lattices realize it, but I'm not 100% sure. In any case, fewer, even less is known about that. Okay. And with regards to this quantity, there's a fundamental theorem that I want to tell you about. First, let's define the dual lattice, which you've already seen in your exercises. L star is given a lattice L. L star is the points in Rn which have a inner product which is integral with every element of L. So this is called the dual lattice of L. As the name suggests, it's a lattice, and there's easy formulas expressing the lattice. Once you have a basis for a lattice L, you can just take the lattice spanned by the dual basis, and that's going to be the dual lattice. And it's possible to express the covering, to give bounds on the covering radius of a lattice in terms of the shortest lattice vector in the dual lattice. And that's the content of the theorem that I want to tell you about. So this is called the Banachek transference theorem. As you can see, I prepared my lecture carefully and I spelled Banachek. So it's a Polish name with a string of 6 consecutive consonants, and I'm very proud of succeeding of remembering the order of those consonants. So so this is a fundamental result from 1993, and it says the following: for all n, for all L, lattice in Rn, I'll state 2 results. So lambda 1 of L times the covering radius of the dual lattice is bounded above by n. 2, there exists a constant such that for all L, all I, all n, lambda I of L times lambda n plus 1 minus I of L star is bounded above by constant times n. So both of these bounds are very, very fundamental and important. They sort of formalize this idea that the covering problem, I'm talking now about the first theorem here. It sort of formalizes this idea that the covering radius problem is sort of dual to the packing problem. So if you have a lower bound on lambda 1, it translates by moving over to an upper bound on the covering radius for the dual lattice. I should mention that up to constants, these theorems are sharp. So these results are sharp up to the constant. In other words, there exists lattices Ln in space of lattices of dimension n and a constant C prime such that lambda 1 of Ln times covering radius of Ln star is bounded from below by C prime times n. So this inequality this inequality here can be reversed along a subsequence of lattices. And notice that the constant here is independent of dimension. It's much easier to get a bound of this form if you allow a constant in front of the right-hand side, which depends on the dimension. But here so Banachuk is telling you exactly how this depends on. Let's say one more word about the importance of this. So the importance of the result is, one aspect of it is that covering radius is very elusive. It's very hard to get bounds on the covering radius. And this enables you to derive bounds on the covering radius from bounds on the packing constant or the lambda 1. And remember that we know how lambda 1 behaves for almost every lattice. We have some information about the expectation, at least, of this quantity as a random variable in the space of lattices. And there's an exercise in your exercise sheet that if you choose L at random according to the Haar-Siegel measure and look at its dual, then the dual lattice is also being chosen uniformly at random with respect to the same measure. In other words, the mapping that takes L to the dual lattice L star preserves the Haar-Siegel measure. So if you know something about lambda 1 for almost every, or for a large probability of lattices, then you know another fact about the covering radius for the dual lattice, which also gives you the same bound on the measure. So that's one reason for the importance of this theorem. The way it gives you a way to attack this covering radius problem. And another reason for its importance is computer science. So if you remember the lecture last week, I said that the two problems of interest in computer science are called the shortest vector problem and the closest vector problem. They're both related to each other, and it's very important in some applications to get connections between these two problems. In particular, I said last week that one of the main reasons that lattice cryptographic protocols are so interesting is that they have something called the worst case to average case reduction. So the average case problem is as hard as the worst case in these problems, which is not something that often happens in other hard problems in computer science. Some of the proofs of that fact and some of the analysis of that fact rely heavily on this in this inequality. Okay, so those are the reasons to be interested in this theorem.
Sorry?
Yeah.
Can I ask you, do the lattice L and its dual lattice become statistically independent in some sense? Do you know that? If you have
I think this exactly says that the answer is no, right? I mean, if you have some information about where L is in the space of lattices, these inequalities give you information about where L star is. Yeah. And we're sort of making that connection quite tight.
Yeah, good.
Okay, so this is the theorem. So I'm going to, hopefully I'm going to have time to sketch the full proof of 1. I'm not going to talk about 2. I just mentioned it for education. So we're going to be discussing the proof of 1. And the proof relies on ideas from harmonic analysis, from Fourier series and Fourier transforms. So in this first lecture, I will just give you some background in Fourier analysis. So I'll just, without proofs, I'll just tell you some facts. So it's like a crash course in on Fourier series and Fourier transform. And since it's a crash course, so all of the facts that I'm telling you are going to be valid for some classes of functions f, which might vary from one statement to the next. And I'm not going to be looking for, so we won't strive for full generality. What I mean by that is we're going to be discussing some facts about some functions having a convergent Fourier series, and we're not going to care about how general that phenomenon is. So let's start with, so there are going to be 4 pieces. One is going to be the Fourier series on the standard lattice, namely Rn over Zn, or in other words, Zn periodic functions on Rn. Then we're going to move on to the general lattice and still talk about Fourier series. Then we're going to talk about Fourier transform, and then we're going to connect all of that. So let's start with Fourier series on Tn, which is Rn over Zn. So let f be a C infinity function on Tn. So what does that actually mean? Another way of saying that is that f is, and in this talk, functions will be complex valued. It's just more convenient when you're talking about Fourier series to talk about complex valued functions. So f is a complex valued function on all of Rn, which is Zn periodic. So the value at every point is the value at the same point plus an integer vector, and it's C infinity. That's sort of the meaning of C infinity here. And so the exponentials, I'm going to use this notation. If y is a vector in Zn, E y dot x is just notation for e to the 2 pi I inner product x and y, where this is the standard inner product. And let's define f hat of y given a function f to be the integral of f of x e to the minus x dot y dx. A few words about notation here. And so first of all, this is a different hat. So not to be confused with the hat that we already saw, f hat that we already saw in the Ziegler summation formula. We're using the same notation, even though these are different things, because that's just the conventions in this field. The second thing to say is, what is this measure dx on the torus? So this is the Haar measure, normalized Haar measure. So if you don't know what it is, this is just, you just think of this torus as being 0, 1 to the n, and dx is the Lebesgue measure restricted to 0, 1 to the n. Or in the language that we used, we're choosing a fundamental domain for the lattice, and we're looking at the restriction of Lebesgue measure to this fundamental domain. With these conventions, the standard fact about Fourier series is that you can recover f of x from f hat of x. And this is called the Fourier inversion. The f hat of y are the Fourier coefficients, and this is a representation of f as a Fourier series. So this is the basic identity. Please stop me when there's something you want to ask. Let's do the same thing for a general lattice or a general torus. So let's take L to be a lattice. I didn't assume that it's a covolume 1. And let's denote by T with an L below the quotient torus. So this is Rn divided by L. And let's take a function on this quotient torus, which is a C infinity function. So that's defined in exactly the same way. It's a C infinity function on Rn, which is L periodic. And let's define the Fourier transform to be using the same formula, but now we have to sort of understand it a little bit better. So we integrate over this lattice TL. I'm sorry, dx. But now y should belong to the dual lattice. And the reason we want to take y belonging to the dual lattice is if you think about these exponentials, functions, recall that the exponential function, if you have a 2 pi I here, if you add integers to this number, you're not changing the exponential function. So if you want this to be a well-defined function on the quotient, it should transform correctly when you change x by x plus an element of the lattice. And that's exactly saying that y inner product with an element of the original lattice is an integer. So it's sort of natural to restrict this to elements of the dual lattice. And this dx is the normalized Haar measure on this torus. So let me write that down. So this is dvol divided by covolume L restricted to a fundamental domain for L. Or if you want, maybe I should have said this earlier, this is just a Haar probability measure on this quotient. The quotient is a compact abelian group, so it has a Haar measure, and since it's compact, you can normalize it to be a probability measure, and this normalization exactly ensures that this measure becomes a probability measure on this quotient. Okay, so that's the meaning of this symbol dx. It's the normalized Lebesgue measure. It's not exactly Lebesgue measure, it's Lebesgue measure multiplied by a scalar to make this into a probability measure. All right, so that's the definition of the Fourier coefficient, and then we have the same formula. So f of x equals some so we can recover f as a series, as Fourier series involving its Fourier coefficients. Okay, so that's the shape of Fourier series on a general torus. Now we have a third construction, which is the Fourier transform. So the Fourier transform doesn't work on tori, which are compact. It works on Rn. Also, you can think of it as an abelian group. But now the exponential functions, what abstractly the exponential functions are so-called characters on the group. So on Rn, we have more characters, and somehow we have something called the dual group, which is Rn itself. And so here's what this looks like. So if we take f, which is compact, which is infinitely differentiable, and I'll just write down the words. It's a Schwartz function, so I'll write down what this means, although we won't get into this. So so every derivative of f of every order decays subpolynomially on Rn as the norm goes to infinity. So what I mean by that is you take any, so f is a function on Rn, it's infinitely differentiable, so you can take any number of partial derivatives. You take any partial derivative and you evaluate the absolute value of the partial derivative, as you increase, as you go away from 0, this goes to 0, and it goes to 0 faster than any function of the form norm of the vector to some power. So that's what a Schwartz function is. And this is the class, happens to be the class on which everything that I'm saying is well defined and works best. If you want to talk about more general functions, then you have to, be more careful. Okay, so this is the class of functions, and now we define the Fourier coefficient or the Fourier transform. Again, I'm using the same notation, f hat of y. F hat of y is the integral on Rn of this exponential. So it's exactly the same formula. Here, y belongs to Rn. Any element of Rn can be used. And the function, the derivative exists because it's a Schwartz. The reason for choosing Schwartz functions is just to be sure that this infinite integral actually converges. And in fact, as a function of y, you get a Schwartz function back. So that's sort of the point of these Schwartz functions. The transform, if the original function is smooth and rapidly decreasing, then so is the transform. And then the Fourier inversion formula says the same thing. Formally, it just looks the same. So f of x is the integral on Rn, f hat y exponential yx dy. And I should have said dy and dx are the Lebesgue measures here. All right, so that's Fourier transform. Let's just give two formulas that we're going to need and an example. So an easy formula, which you can check. If you have a function f and you define a new function h by the following formula, so I'm rescaling the argument of f by lambda, and I'm increasing the output of f by lambda. And this is just this rescaling dilates the graph, and this rescaling ensures that the integral doesn't change. So this is sort of what kills the Jacobian. If you do a change of variables formula, h and f are going to have the same integral, but they're different functions, and you want to know how the Fourier transform behaves, and the answer is that the Fourier transform of h is the Fourier transform of f evaluated at y over lambda. And this is proved by a computation. It's just a change of variables in the definition of the Fourier transform. And we're going to be using a very important function, and the function is the Gaussian. So rho of x is e to the minus pi norm of x squared. So this is called the Gaussian. And it's important because it satisfies the following formula. It's equal to its own Fourier transform. So this is the only non-trivial function with this property. And so if we plug in the previous formula, we're going to be using this Gaussian again and again in what follows. So if we use the previous formula, and if we define the Gaussian with parameter S, to be rescaling x by a factor of s in the formula, then this is what you get. The Fourier transform of rho is s to the power n times the Fourier transform, the original function rho scaled by 1 over s at y. Okay, so that just follows from this fact and from this formula quite easily. And we're going to need this. I'll say why soon. And the fourth piece of information that we're going to need is a connection between Fourier series and Fourier transform, which is the Poisson formula. And I'm going to give it in the general case. General means on Rn for general lattices. So Poisson summation formula, which I'll abbreviate by PSF. It says the following thing. If you have a C infinity function, which is say a Schwartz function, or maybe compactly supported, maybe I should have said this is a Schwartz function here. This it's one of these nice functions. So given such a function, what you can do, and given a lattice, what you can do is you can periodize the function. So define the periodization of f by FL of x is the sum of v in L plus x, f of v. So in other words, we sum the function over all the at point x by all the translates of x by elements of the lattice. And so we're forcing this function to be periodic. So now FL is L periodic. FL is L periodic. You could worry about this convergence of this series. So please don't worry about the convergence of the series. I mean, this is sort of one of the reasons why we're taking this rapid decay, or if you like, you can just think of compactly supported functions. So this becomes a finite sum. So FL is L periodic, and we can look at its Fourier coefficients and its Fourier expression as a Fourier series. And so then what we have is that we have this. If L is of covolume 1, and we have an almost identical formula except the covolume of L star in front. For general L. So that's the Poisson summation formula. So how is this Poisson summation formula different from the formula for the Fourier series? It looks exactly the same. It has exactly the same shape, especially if the lattice is of covolume 1, except that we took the Fourier coefficient, which is the Fourier transform of f. And this is the function, this is the periodized function. So if we were using the Fourier series, this should have been the Fourier transform of FL, but instead it's the Fourier transform of f. It's the function before periodizing that appears, and this f hat, which appears here, is the integral, is the definition of the Fourier transform of Rn, okay? Not the Fourier series coefficient. Okay, so they're very similar looking, and that's intentional. They formally they look almost identical, and into the proof is also quite easy. Let's prove this. So we want to compute. So let FL be the periodization of F. Sorry, periodization of F. We want to compute the Fourier coefficient of FL for Y, an element of the dual lattice. So let's do that. So FL hat Y is the integral on TL of this thing. That's just the definition of the Fourier series, the hat appearing in the Fourier series. Now I want to stick in the definition of the periodization. So this is the integral over TL of the sum Z and L, f of x plus z. So this is the definition of FL. Now, the function is nice, so I can do some manipulations with these series and these integrals. So of course, I'm not justifying that formally, but I hope you won't mind. So I'm going to exchange the order of integration and summation here. And now I'm going to change the integrand by replacing x with x plus z. Okay, and the reason that I can do this is that y belongs to L star and c belongs to L. So if I had an x here and now I have an x plus z, the difference between this and this is the inner product of y with z, which is an integer, and it doesn't show up in this exponential formula. And this, so what we're doing now is we're integrating this function over the fundamental domain of the lattice L, and then we're translating it around by lattice points. So in total, so maybe I'll add one more line here. So this is the sum Z and L. Here we have 1 over the co-volume of L. Here we have, let me write FL. Well, maybe not, F is maybe a little bad letter. Let's write omega L, f of x plus z e to the minus yx plus z d vol of x. And omega L is a fundamental domain for L. So that's just the definition of the integral inside. And so this is what this is a integral on a fundamental domain, and then we're translating the fundamental domain around by all integers. So at the end of the day, we get 1 over the co-volume of L times the integral over Rn of f of x e to the minus yx d vol x. And this is the same as co-volume of L star. So you can take it as an exercise. The covolume of the dual lattice is 1 over the covolume of the lattice. And this is the formula that we had before for the Fourier transform of f at y. And now plug into the Fourier series for FL. So this was a proof of this Poisson summation formula. Let's sort of give a snappy notation for this formula, which we're going to use later. Notation for a countable set, called it lambda, in Rn. F of lambda is defined to be the sum of f of x over the elements of lambda. And with this notation, the Poisson summation formula becomes the following formula: f of x plus L, summing the function f at L, which is just the periodization of x. This is FL of x, if you want. This is the covolume of L star times, that's what we had before. And the simpler case, x equals 0, the right-hand side simplifies and we get f of L equals the covolume of L star times f hat of L star. So this is the easiest version of the Poisson summation formula at the point x equals 0. And let's just record two formulas for the function that we had in our example, using the function rho sx, the Gaussian with weight s. We're going to get two formulas, which I'm going to call 1 and 2. So rho s of L okay, I just specialized this formula became formula 2, and this formula became formula 1 for this particular function for which we've already computed the Fourier transform. Okay, so these two functions are going to, these two identities are going to play the important role in the proof of this Banachek transference theorem. Okay, so let's take 10 minutes and I'll show you the proof. All right, can you hear me? Okay, so let me, so what are we proving again? We're proving this Banachek transference theorem. Let me just show you the theorem again. So it's making a connection between the, am I sharing my screen? Yes, I'm sharing my screen, right? Yeah. So we're making a connection between the covering radius of a dual lattice and the shortest lattice, the shortest vector in the primal it's called lattice. And let me sort of explain the geometry. It's a simple proof, as you'll see, but I want to explain the reason it works, maybe, or some of the intuition behind it, because it's actually this was an open question for a long time, and Banachek had the intuition that the Gaussian was the correct thing to look at. And I want to sort of give some ideas about why that's true before doing the proof. And so the reason is, there are two reasons why the Gaussian works. The first is that this Poisson summation formula, the fact that the Gaussian is equal to its own Fourier transform, makes the connection between, where did this go? Makes the connection, for a general function, what should have appeared here and appeared here shouldn't have been the same function. There should have been a hat here. So the reason that we can make a connection between the function evaluated on the lattice and the function evaluated on the dual lattice is just because the same function. That's just because the Gaussian is self-dual. But a more important factor is that you can figure out how these quantities behave when you vary S, and that's the main point. So let's think about this for a moment. So this quantity is measuring the period. This is the periodization of the Gaussian. In other words, if you think about the torus has a special point which is 0. It's sort of the origin of the torus. It's the coset of the identity, if you think about it in the torus. And this is the sum of the periodized, this is the value of the periodized function at the origin, and this is the value of the periodized function at all the other points. And so let's draw a little picture. So maybe I'm drawing a one-dimensional picture. So maybe this is the Gaussian. And when you change, this is the Gaussian for one value of S. When you make S bigger, so maybe this would be rho. Let's take a different color. And if we make S bigger than 1, we're squeezing down the support of the Gaussian. So it looks like that. So this might be rho S for S bigger than 1. And when we decrease the value, this would be rho S for S smaller. I'm sorry, the picture is wrong because I've only done the scaling in the X coordinate and I didn't do the scaling in the Y coordinate. I'm supposed to scale things so that these functions all have the same integral, as I said earlier. So just a second. So this should be.
But you did not scale the function in its definition.
Oh, yes, thank you. Why didn't you tell me this before so that's fine. Actually, that's cool. I know I've gotten better at using this thing. Here we go. All right, so yeah, so that's what happens to the function rho S as you vary the parameter S. So the smaller S is, the more spread out the function is. The bigger S is, the more localized it is. And the property of and what we're doing is we're summing, let's just do a picture. If this is, say, 1 and this is -1, and we care about this quantity, or this quantity, what we're doing is we're summing sums of Gaussians. Oops.
But I think the cases are different. The red one is the case S is less than 1.
Yes, thank you very much. You're right. Wait. Now I've confused myself. So if X is 1, and so the value of the red guy at 1 should be the value of the blue guy at S. So if S is less than 1, then this should push out. Yeah, so I'm saying this. Is that what I said before?
This
I
is what it
managed to
is.
I managed to confuse myself. So if S, so let's see, the value of the green line at 1 is the value of the blue guy at S, which is bigger if S is smaller than 1. So I think this picture is now correct. Do you agree? Yeah. All right. So I'm just drawing the graph for the periodized function in case S equals 1. So maybe this is the this is rho S at x minus 1, and this is another graph localized rho S at x. Sorry, this is at x plus 1, this is at x minus 1. And so when you sum them up, you're getting the sum of these waves. Okay, that's these periodized functions that are appearing here. All right, so there's a picture that I stole from Oded Regev's course, Oded Regev's homepage. Oded Regev is a computer scientist who developed all of this in the computer science literature to quite an impressive degree. And so this is the Gaussian summed up over a lattice for a value of S, which now I've forgotten whether is small or large. So sorry, as
Large
S
probably.
for a large value of S. Okay, so it's very localized at the lattice points. Now we're decreasing the value of S, and these peaks are getting flatter, and there's a kind of a special time when you see the peaks, but they're starting to interfere. And this time they're interfering so much that the function has become constant. Okay, so that's this transition that occurs. And the main point about this, as you'll see from the proof, the main point is this transition from having very well-defined peaks to having hardly at all defined peaks, an almost flat function, involves a very small change to the parameter S. So in a very narrow strip for the variable S, you transition from this picture to this picture. This picture appears only for a very, very small range of values of S. That's the point that comes up in the proof, as you'll see. All right, so let's, at least that's in my opinion, that's sort of the main geometrical point. All right, let's do the proof. It's a series of lemmas. So lemma 1, for all L, for all S. So L is always a lattice. S is, I'll just write that down first, but then L is always a lattice in Rn. Sorry. For all L, all S is a positive number. For all X is a point in Rn. Rho S of L plus X is less than or equal to rho S of L. So this is saying that the maximum of these peaks is attained at the special point to 0. So if you think about this sum, and you think about the sum of the purple lines, the max, of course, it's a periodic function, and its maximum is on the coset of 0. That's the content of 1. By the way, this will not be true if the purple line were, for example, an indicator of a ball or an indicator of a set, right? And if you take the indicator of a set and the set is localized around 0, and then you change the parameter, the set is growing, suddenly these translates start intersecting each other, and they become larger at some point inside the quotient, which is not 0, and you don't understand what it is. But for Gaussians, no matter what the value of the parameter S is, the maximum is always achieved at the origin. So what's the proof? So we're adding real numbers. So this is a real number. And so let's evaluate this real number. So this is, I'm using formula 2. So this was, formula 2 was a formula for this quantity, which is exactly this quantity. And since they're real numbers, I can write it in this form. And now I'll push the real number inside as far as possible. So
are you looking only at covolume 1 lattice here, or did you miss
thank you. Yeah, there should be a covolume, right? So let's write alpha to be the covolume of L star, and let's divide by alpha. Okay. So oops. S is real, rho of 1 over S of Y is real. And so the real value pushes inside the sum. And now I'm going to use the fact that so this is a real number. This number here is a real number between -1 and 1. And now I'm going to use the fact that this is a positive number. And so this is less than or equal to S to the n sum Y and L star rho 1 of S of Y. This is because rho 1 over S of Y is positive. And this is really a feature. The fact that the transform is positive and the fact that it's real is really a feature of the Gaussian that we're using here. And by formula 1, this is rho S of L divided by alpha. So if you divide through by alpha, you get divide through or multiply through by alpha, sorry. You get the lemma. All right. Lemma 2. Now let's assume S is at least 1 for any L and any X. We have this. So I'm comparing rho on the right to rho S on the left. And I'm saying that I just have the price that I have to pay is S to the power n. Proof. By the previous lemma, we have this. So we just need to prove that rho S of L is less than Sn times rho of L. And if we set, again, alpha to be the covolume of L star, rho S of L is alpha times S to the n times rho 1 over S L star. That's formula 1. This is the definition. And I'll just insert the definition of the Gaussian. And the Gaussian goes down when we change the parameter. So this is what was confusing me before, and it's still confusing me. So I'll just write it down and you'll tell me if my notes are okay. So if S is greater than or equal to 1 and you decrease S, then you increase the value of the Gaussian. So I think this is okay. And this is the same as alpha S to the n. Just so using again 1. So we get, so this implies the inequality that we want. Dividing through by alpha, divide through by alpha, you get the second lemma.
I don't think you need to divide by alpha. The alpha disappears.
Oh, sorry. Thank you. The alpha here disappears. Thank you. All right. Lemma 3. So now what I'm going to do is I'm going to compare the sum of the Gaussian on a translate of the lattice, and I'm going to take the same set and remove a ball. So, okay, so let's write it down. So I'm taking the lattice, I'm translating it by x, then I'm removing a ball. The radius of the ball is square root of n. That's what's going to be valuable in the proof. And the gain is bounded above by 1 over 2 to the n. So this is a property of the Gaussian. Notice that this is, the S here is taken to be 1. Okay, so this is somehow like a decay property for the Gaussian, but this doesn't care about the lattice, about the co-volume of the lattice. So this is saying that this is true for lattices that are dense and for lattices that are not dense. It holds true in both cases. So let's, this is sort of an important lemma here. So what we're going to do is we're going to work with row 2, the Gaussian with parameter 2. For any lattice L and any X. So let's use, so I'm going to write down a series of inequalities and then justify them. So I'm claiming that 2 to the n times rho of L is greater than rho 2 of L plus X. So that's lemma 2. Let's scroll up to lemma 2 just to see. So lemma 2 says this. And if I use the lemma with S equals to 2, I get this. Rho 2 of L plus X is obviously bigger than rho 2 of L plus X minus the ball of radius, minus the value, minus the sums over the ball of radius 0. Now that sounds like a very, very wasteful bound, but it's a bound. And let's write down what this means. So this is the sum over y's in L plus X of norm bigger than square root of n, e to the minus pi y over 2 squared. And I'm going to write this, I'm going to multiply and divide by, well, you'll see. By e to the minus pi y, norm pi y squared. So this becomes e to the 3/4 pi norm y squared times e to the minus pi y squared. So I just multiplied and divided by e to the pi norm of y squared.
The sum should be over y greater than square root of n.
Sorry. All right, and so now what I'm going to do is I'm going to replace each of these elements by the smaller value, which is when you let y equal square root of n. So this becomes e to the 3/4 pi n sum this. And this is e to the 3/4 pi to the power n. And this is what we're calling rho of L plus X, set difference, ball of radius, square root of n. Now, E is approximately 2.7, pi is approximately 3. So this is, this number is, it happens to be bigger than 4. In fact, it's close to 10. E to the 3/4 pi is close to 10. But in any case, what we care about is the fact that it's bigger than 4. So this is greater than 4 to the n times this. And now let's look at what we have. So we started with 2 to the n times rho of L, and we ended with 4 to the power n of this quantity. So moving the 4 to the n to the other side, we get the inequality that we want. All right. Let's record a corollary of this. So if L is a lattice and its shortest non-zero vector has length bigger than the square root of n, then summing the Gaussian over the non-zero lattice points gives us the following bound. Okay, let's see why that's true. So first of all, this inequality here is true. I mean, this 2 to the minus n is smaller than a half, so this is true. Can you hear me? It says my connection is unstable. Yeah, okay. So, so proof. The point is that when you're summing over the lattice points other than 0, that's the same as summing over all the lattice points that are not in the ball of radius square root of n because of this assumption. And by the previous lemma, this is less than or equal to 2 to the minus n rho of L, but rho of L is 2 to the minus n 1 plus rho of L minus 0, because the Gaussian has value 1 at the origin. So the difference between summing over all the lattice points and summing over all the non-zero lattice points is just the value 1. Okay, so now if you move the 2 to the n over, you open this up, move it to the n over and rearrange the sum, you get this. So rearranging gives the corollary. One more lemma. Again, let's assume that the shortest vector in the lattice, non-zero lattice, has length at least square root of n. Let's look at the difference between the value of rho on the coset of x divided by the covolume of L minus the constant function 1. So the this number is the number 1. It's a constant number. And this is a periodized function on the dual lattice. And we're saying that this periodized function is close to this constant function in sup norm up to a small number. Okay, that's the content of this lemma. Recall, okay, so let me prove it and then I'll make the connection to the pictures that I showed earlier. So by formula 2, the I'm applying formula 2 to the dual lattice L star. I don't remember if this should be a covolume of L or a covolume of L star. Let's look at the formula 2 again, sorry. Oops. Formula 2. Covolume of L. This divided by yeah. Okay, this is correct. So formula 2 says that this is equal to this. Again, this is formula 2 with L replaced by L star, and of course, the dual of the dual L star of L star is L by the fact that this is generated by the dual basis. So we have this inequality, and so let's open up this formula. So this is there's a contribution at the origin, which is 1, and then there's the rest of the sum. And so we're interested in the difference between this and 1. So we're interested in this thing. And so the second summand satisfies this. And this is because all the row i's are non-negative. So if you use the triangle inequality and open up this expression, you're going to get the sum of the row y's times 1 on the non-zero. Let me do that in one more line here. So this is the sum. And here I've used the fact that rho of y is everywhere non-negative. And so this quantity is at most 1. And so this is less than the sum of rho of y over the non-zero lattice points, which we're denoting by this. And this is less than 1 over 2 to the power n minus 1. That's the corollary that we had before. And so if you look at what we claimed, that's exactly what we claimed. Okay, so let's now do the proof of the theorem. Maybe before the proof, let's just look at the conclusion of this lemma. So here we're assuming that the shortest vector in the lattice, non-zero lattice, has length at least 1 over n, and we're getting that this function is essentially constant. So if we go back to the pictures that I showed you before, these pictures. So in the situation that the shortest vector in the lattice is of length square root of n or more, the picture that we're supposed to see is this picture. If we use the standard Gaussian with s equals 1, and we use such a lattice, we're seeing a function which is almost constant. That's the meaning of the fourth lemma. But on the other hand, if we look at, okay, so you'll see in the proof that it's easy to derive a contradiction from that. So assume by contradiction that for some lattice L, the product of the shortest non-zero vector in L and the covering radius of the dual is bigger than n. So we want to contradict that. Rescaling L by a factor of c rescales L star by the corresponding factor 1 over c, because they're dual lattices, and the definition of the dual lattice, if you multiply everything in one side by c, you need to multiply everything on the other side by 1 over c. And so we can do a rescaling we can assume, and also these numbers, lambda 1 and covering radius, they obviously scale by c to the power 1 over n when we rescale the lattice by c. So if we replace L by c, we're changing this by c to the n, and we're changing this lattice by c to the minus 1, so we're changing the covering radius by c to the minus 1 over n. So we can choose the appropriate c to assume that these two things are equal to each other. And since their product is bigger than n, each of them individually, since they're equal, is bigger than square root of n. And so this is the assumption of lemma 4. So the function x maps to rho of L star plus x is very close to a constant for all x up to error 1 over 2 to the power n minus 1. That's what the lemma said. So let's record it in the following way. That is, for all x and y in Rn, if we look at the quotient of the values of this function at two different points, we get the top is at most alpha, where alpha is the covolume of L times 1 plus 1 over 2 to the n minus 1. And the bottom is at least alpha times 1 minus 1 over 2 to the n minus 1. And alpha is the covolume of L. And this is alphas cancel, and this is less than 2. So the variation of this function for any two elements, y and x, the quotients vary by at most 2, so it's almost a constant. But on the other hand, since the covering radius of the dual lattice is at least square root of n, there's an x in Rn such that the distance between x and the dual lattice is bigger than square root of n. In other words, if we move the lattice by x, if we translate the lattice by x, any such y has length at least square root of n. So if we plug that into lemma 3, oops. We get this. So what did we got? What did we get? We got that yeah, and on the other hand, so we got that and rho of L star is rho of L by the, I'm sorry. Wait a minute, I confused myself for a moment. So at this particular x, yeah, at this particular x, yeah, this should have been an L star. That's what's confusing me. So rho of this quotient is bigger than 2 to the n. So so now we got a contradiction. Right here I've said that these quotients for every y and x, these quotients are bounded by 2, but now I'm doing the same thing with minus x and 0, and I'm getting a number which is bigger than 2 to the n, which is a contradiction. So this proves the theorem. So the contradiction somehow comes about by saying that at the same time, because of this bound, the function is essentially constant, but because there's a point far away from the dual lattice, it can't, very far away from the dual lattice, it can't be essentially constant. And that proves the theorem. Okay, so this is all I've prepared for you. So thanks for the attention. Thanks for keeping me honest. That's enough for this semester. Have fun with the exercises, those of you who are taking the exercises. Okay, take care, everybody.
Can I quickly ask you something?
Yeah, definitely.
Regarding lemma 3.
Yeah.
I am a bit, I don't understand why it is true. I do agree with the proof.
Okay, that's a good start.
But somehow, can you say something? So we shift this set, and what does it say? It says that there's a lot of cancellation coming from the exponential terms outside, which are large.
No.
Or
It's
what is happening?
I don't think it's the cancellations. There are no cancellations because all of the signs of the Gaussian are positive. So there really are no cancellations. This is just saying that L plus X, sorry, the Gaussian is sufficiently decaying rapidly so that no matter how you sum it up, you're going to have, if you remove points which are near the origin, you're going to have very little, the contribution is going to be small. Okay, so
right. It's just straightforward.
There's somehow there are two regimes here. One regime is when notice that the co-volume of the lattice is not 1, right? So somehow you can think about this in two regimes. You can think about the lattice being very, very sparse, so points being very, very far away from each other, or you can think about the lattice being very dense, and this becomes more interesting when the lattice is, let me think for a moment. This becomes, I actually prepared
it's most interesting in the middle, no? Because I mean,
I think it's interesting when the
very
lattice is very dense somehow. Sorry, why were you saying in the middle?
I mean, if it's very dense and it's really just then you really, like, you're approximating the sum by an integral, basically.
Right.
And then it becomes, and if it's very sparse, then the vast contribution to the sum is just at the point 0.
Right.
So it's kind of uniformly.
Yeah. There's something going on in the middle, and the proof somehow utilizes the relationship between 2 and 1, right? That's how the proof works.
Mm-hmm.
I mean, somehow the Gaussian has a certain specified rate of decay when you change the parameter just by a factor of 2, which is kind of the main point. All right. Okay. Nice to see all of you. Take care, be healthy, and have good fun with the exercise.
Tada Rabba. Thanks. It was cool.
Thank you very much.
Bye.
Bye.